Good morning. My name is Luka Romano. I'm an undergraduate student at Universidad Nacional de Córdoba. I'm currently working at UNITEFA, Unidad de Investigación y Desarrollo en Tecnología Farmacéutica, CONICET, Argentina. I'm here to present the e-poster titled Synthesis, Optimization, and Characterization of chitosan nanocapsules for Delivery of Cannabis Extracts. As an introduction, we know that cannabis sativa is composed of more than 100 compounds, such as terpenes and cannabinoids, like delta-9 THC and CBD, which are extracted in cannabis alcoholic extracts, CAE. One strategy for CAE delivery is chitosan nanocapsules, which have an oily core and hydrophilic shell. These offer biocompatibility, biodegradability, and mucoadhesiveness. We will focus on nanocapsules formulated with olive oil as the oily core, which we refer to as olive chitosan nanocapsules. The objectives of the study are the optimization of the synthesis of a CAE carrying nanocarrier to characterize its physicochemical properties and determine its encapsulation efficiency. In terms of methodology, the synthesis of these nanocapsules was done via the solvent displacement method. The first step consisted of mixing the aqueous phase, composed of a solution of 0.5 milligrams per milliliter of chitosan, and organic phase, which consists of acetone, 280 as a surfactant, and CAE dissolved in olive oil, to obtain a suspension of nanocapsules, which we then subjected to homogenization, to get a uniform population of nanoparticles in terms of size. Then, the samples were left overnight to ensure acetone evaporation, and centrifuged to obtain a supernatant of nanocapsules, which were then isolated. The next step of the methodology consisted of the optimization of the synthesis process via Box-Venken factorial design, using Minitab 18 software, and later, the characterization of various parameters via dynamic light scattering, high-performance liquid chromatography, and scanning electron microscopy. Moving on to the results section, in synthesis optimization, we can observe a Pareto diagram, which shows the influence of synthesis parameters on nanocapsule size, which are concentration of chitosan, CAE oil volume, and 280 volume. We can see that some of these parameters cross the dashed line, which indicates that they have a statistically significant effect on the size of the nanocapsules. Due to time constraints, only the results for size are shown, but this was also done to evaluate the effect on polydispersity index and set potential, although this last one was not affected by any term. This let us fine-tune the synthesis to obtain a ratio of reactants that enabled us to synthesize a nanocarrier that had adequate nanometric characteristics, which will be discussed later. DLS analysis was done to evaluate these aforementioned characteristics. Size versus intensity graphs show that these nanocapsules had a consistent nanometric size of 231 plus minus 4 nanometers, for the dispersity index of 0.18 plus minus 0.02. That means that our population of nanocapsules are monodispersed, and set potential of plus 33 plus minus 1, which provides the colloidal stability to ensure nanocapsules' long-term stability. ACM analysis was also performed and allowed us to see that nanocapsules possess a spherical morphology, which enabled us to validate DLS results as legitimate. Lastly, an HPLC methodology was developed, which allowed us to selectively separate and quantify cannabinoids present in the samples, although we will only focus on CBD. This was used to evaluate the encapsulation efficiency of the nanocapsules by an indirect and direct method. This showed that the system was able to encapsulate 99% of CBD from the CAE. In conclusion, the results show that the synthesis of the proposed nanosystem was effectively achieved, with suitable nanometric parameters and high encapsulation efficiency. We would also like to acknowledge these institutions who provided funds to complete our research.